All right, so in this video, we're going to be continuing with our analysis of time series, and we're going to work our way toward creating ARIMA models, autoregression, integrated, and moving average models. So we're going to pull in a new data set, air passengers. And we're going to look at our air passengers data set and kind of inspect it. And again, this is the number of air passengers starting in 1949, month by month, up through 1960 only. And we're going to then plot this data. And we can see that between 1949 and 1960, the number of air passengers per month, whatever unit these are in, was steadily increasing. But you can also see there is kind of a seasonal component that seems to be getting stronger over time. So we're going to begin by decomposing our air passengers data. So we'll just call this decomp 1. And then we're going to plot that decomposed data. And so again, we can see our original observations at the top. Our trend seems to be gently sloping upward for the most part. We can see our seasonal component that again does seem like there is a stronger seasonal trend as the data goes on, but this smooths out that analysis at the beginning. That does seem to make the random component seem a little more autocorrelated, random walkie type thing, a little more random in the middle, and then again, still kind of exhibiting something of a seasonal component. So this is essentially an average of the seasonal component, and we can see that even though there is some sort of seasonal properties, it is a seasonal component that is changing over time, and so it is strongest in the middle, where the best match is in the middle, where it sort of cancels stuff out, and where it starts to really fail is where you see this sort of non-random pattern kind of appear in our supposedly random residuals. Now we can analyze our data set for our assumptions that we're making about the data by doing some common statistical tools, QQ plots, histograms, and then also our ACF and PACF graphs. So we're going to start with the histogram. This does not seem to be terribly normally distributed as it is, although we could then plot, for instance, from our decomposition, we could plot, for instance, that random component and see if that at least meets our normal distribution. It seems a little more spread out, but I guess it's not too terrible. We could look at our normal probability plot, again, for the original data. I spelled something wrong. That's because I have a P where it doesn't belong. This looks like it has quite a strong tail on the bottom end, which isn't great. Let's look at the random component. Again, we have a little bit of a thing that doesn't look normal at the one end. But I don't think this thing at the end is as strong as the one on the bottom of the previous example. And then we can also look at the ACF. And the PACF. Now, again, this is to help us calculate the number of lags we would need for the moving average. And it looks like we still have strong relationships really well past a year out. But when we look at the PACF, we see that it's basically just 1 month out when you account for those other lags, possibly 2, since this is below the statistical significance line. But you don't necessarily want to include all of these just to get to this one that's way out here. So we would maybe include 2 of these steps in our model. Now, if we want to build an autoregression model only, sometimes referred to as an AR model, normally we specify the number of lags we're going to use. So an AR1 model would be an autoregression model that uses only 1 lag. So we'll call this just AR. And then we'll use a function called ARIMA on our air passengers data. And the order we have to list as a vector because we have to specify 3 components. So in the ARIMA model, the AR component is the autoregression component. That first number tells us how many lags there are. The I is the integrated component that tells us essentially how many times we had to do differencing in order to get to a stationary model. And the MA is the moving average component that would go in the final piece. So here we're just doing an AR1 model, autoregression with 1 lag. And then we can print the model. And if we look at our coefficients, essentially that we have an intercept of 278, and then the autoregression component is basically saying using the previous value in your time series, there is multiply that value by 0.96 and add that to the intercept, and that will tell you what your most likely prediction for the next value in the time series is. Now, it also gives us standard errors on both of these values. And notice that the AIC here is about 1428. When we compare this model to other models, we'll use this AIC model to compare models to see which one is better. A lower AIC is better relative to a similar model on the same data that is higher. But you can't really use this to compare completely different data sets. Unlike R squared, where we say, oh, you want to be close to 1 all the time, in this one, with the AIC, you can really only compare to other models on the same data set. So there's not like an absolute goal that you're trying to reach. Now, we could go ahead and create a time series plot for our air passengers. And then we're going to use the model we just created and compare that So we're going to take our air passengers minus the residuals of our AR model. So these are going to be the fitted values because we're going to take out the errors essentially. That's because I left off an S. There we go. And then we're going to add this to our graph. And so you can see there's a little bit of a lag, an adjustment, but it does seem that other than that sort of being like 1 month off, it does seem to be following the trend reasonably well. But then it's using the auto regression, it's using the previous values. So naturally, it's about a month off. Now, we can also create a forecast to try to predict further into the future. So we're going to make a prediction with our AR model, and we're going to specify how many steps ahead we want to go. And then from that, we're going to extract the predictions. And we're also going to extract the error. That should be an ahead. There we go. And extract the SE. And then we're going to add that to our graph as well. So that was added this little bit of prediction here. And then we're also going to add the confidence bounds. That's the lower bound. And then the upper bound would be the same thing, but with the plus. So here is our prediction right here, but then our standard error, we can see is actually quite wide as we go out further in time, and it keeps getting wider. Now, if we want to look at a moving average, we're essentially a moving average model. We're essentially going to use the same kind of ARIMA model, but we're going to specify a different component. It's going to be order equals 0, 0, 1. Now, moving average model, essentially we're saying we're going to take a 1 month, sort of a window that goes 1 month back, and we're going to calculate the moving average over that time period. So including 1 lag, basically. And then when we print that MA model, again, we get an intercept and a moving average component. So we calculate the moving average, and then we would multiply that average by this coefficient. Now, this AIC is larger, which suggests that this is a worse model than our original auto regression model. But we can go ahead and look at the graph. See how it lines up. and then add that to our graph. You can see the moving average really does okay kind of in the middle. It doesn't do great on either end because it's not really accounting for the trend. It's calculating a moving average. And then similarly, we can also add predictions. So we can predict one value out, or we can predict several values out, let's say 10 steps out. And then as we did before, we can further add these to our graph. Now here we're going to extend our graph bounds a little bit further out so that we can see a little bit more of what's going on out here. So the negative bound and the upper bound for the standard error. And you can see that this moving average, it drops precipitously, and the bounds around that error are quite large. Now we can also kind of compare how well the plots do against each other, how well correlated are the two models in terms of their forecast. They're 95% correlated. We can also look at the AIC values from each of our models to see how they compare. Again, the lower value here will tend to be the better model. And then it's not given in the summary, but we can also calculate the BIC, which is similar to the AIC, but it has a Bayesian aspect. And again, we would generally prefer the lower value would be the better model. Now, we may be able to get a still better model if we were to combine, for instance, the autoregression and the moving average component. Of course, we can also look at other models that we haven't touched on here that maybe use additional lags rather than just a lag of 1 in our model. And again, these are things that you can experiment with. Again, normally you want to pull them out of the ACF and the PACF graphs. But sometimes this is a matter of interpretation. And so you can just go ahead and experiment with some values and see how they do compare to each other in terms of the AIC and the BIC criteria. And I can't spell apparently. Now here we have a coefficient for the autoregression lag and a component for the moving average and an intercept. And this has brought our AIC down a little bit compared to our AIC for the autoregression model only. So that is good. And again, we can go through and we can plot to see how well the model does. So the combination of the moving average and the autoregression doesn't seem to be doing too bad a job. Now we're still getting a very wide margin, and you can see that it sort of escapes the trend as time goes on. So that's not great. but this is common if you don't include a seasonal component in your model. The ARIMA by itself doesn't actually account for a seasonal component. There is a SARIMA model that you can use that will account for a seasonal component, and then you'll actually have multiple things that you have to specify. One set of these components for the seasonal portion, and then one set of these components for just the trend component, basically. So all we're looking at really is modeling the trend. And again, we can look at the correlation. Our previous best model was the ARIMA only, and we can compare this to the ARIMA plus autoregression. So that's a 99%. So it's really actually doing a good job following the autoregression model. And then again, we can look at the AIC and the BIC. And they both appear to have come down since the ARIMA model only. Now, we could also do the same analysis for a full ARIMA model. An ARIMA model with the integrated component would essentially be the integrated is again, the constant there is the number of components you need to take your original time series data into essentially a stationary model. And so that is the middle piece. And so we're going to call this ARIMA and ARIMA. And let's run through that very quickly. Now, one thing that the ARIMA model with the integrated component doesn't do with this package very well is it does not really handle intercepts. So we don't have a constant in this equation. We just have two coefficients that are given to us, one for the autoregression lag coefficient and one for the moving average component. But notice our AIC is now the lowest that it's been so far. So ARIMA, ARIMA, ARIMA. And then let's look at our forecasts. Again, still time series will tend to do this. They get less and less accurate over time. Now, this integrated component basically seems like it's just predicting a straight line, which isn't particularly great. Again, highly correlated with the autoregression model that we started with, and our AIC and our BIC again are smaller. Now, again, we can get better results when we take the seasonal component into account and not just the trend. And so we would need another function for that, a SARIMA model or some kind of exponential smoothing model. We're also going to look at that in another future video. But again, you would do these intervening analyses such as your ACF and your PACF in order to select the number of lags and moving average components that you're going to use. And so you would want to, again, continue doing those analyses, looking at these various components, seeing what you can do and include in order to improve your model. And when you find the best model after some experimentation, then that will be the one that you will want to settle on, or moving on to a different kind of modeling process.